Good afternoon. Good morning, everybody. My name is Tom Malfetto. I'm with ServiceNow's marketing department. And on behalf of ServiceNow, I'd like to welcome you all to this interactive ServiceWatch demo. I'm joined here today by industry veteran Stu Curtis, Senior Solutions Architect at ServiceNow, who will walk you through a demo as well as answer any questions that you may have on today's topic, which is ServiceWatch. And if you have any questions, either post them during the course of the discussion via Join Me. Or if you have any questions after the webinar, or you want to provide feedback or continue this open dialogue on ServiceWatch, please email Stu Curtis or myself. Stu's email is stu.curtis@servicenow.com, or my email is tom.malfetto@servicenow.com. So, as an introduction to the ServiceNow service automation platform on the next slide, okay, so ServiceNow offers suites and applications in three main solution areas of service management and operations management and business management. ServiceWatch offers the capabilities in application development to manage applications, from idea through to support, and to provide simple-to-use building blocks to create custom applications. We'll dive deeper into custom applications later on in the session. And all these applications are built by ServiceNow, and they all utilize the same data model and code base. So because all the applications are built on the same platform, all the metrics and tasks and services and CIs and even assets and people and locations are stored together, really creating a single system of record for IT, or what some call ERP for IT. Some companies call that. In addition, a common workflow engine is leveraged across the applications to bring together people, processes, and automated processes as well. So this allows work to flow seamlessly across the domain areas within IT, which automates tasks, consumerizes the service experience, and helps people work better and smarter. On the next slide, in terms of operations management from the business perspective, if you look at a way that typical data centers manage these days, the focus is on individual technology domains, applications, servers, databases, networks, and so on. There are a number of experts who understand how each of these technologies work individually, and they understand the best way of managing them. So, however, they work in silos most of the time. Few, if any, know of all these IT domains and how they work together end to end. So, business users don't really understand the individual IT components most of the time. Instead, they depend on software-based services to do the jobs. The type of services shown in this screenshot, as you can see clearly. So, because they don't understand application service, firewalls, routers, what's important about ServiceWatch is that these folks, whether email is working, or whether customers can access support portal, or where they can pay the suppliers. In other words, businesses and IT speak different languages, and they have a completely different experience of what IT means. So because of this, IT operations needs to shift from a technology focus to a business service focus. And if they're going to optimize service quality and drive down costs and increase agility, they really have to understand IT operations management from a business perspective. IT needs to shift from the technology focus to a business service focus. If they're going to optimize service quality and drive down costs and increase agility, their own agility. However, existing approaches to doing this just doesn't work anymore in most of the cases, and they can become very expensive to implement and maintain, even if there is limited success. So today we're going to look at these enormous challenges in more detail and talk about how the unique approach of ServiceWatch really changes the game. So with that, I'll turn the presentation over to Stu Curtis.
All right, thanks, Tom. Yeah, so you mentioned a little bit about the gap between the business users who consume the services and, of course, the IT folks who ultimately provide the services. And you were alluding to the fact that IT is still managed by silo. And so what we can see here where ServiceWatch fits in is by bridging the gap between these two areas. So between what the users expect to see, they just want their payroll to run, their email to show up, their reports to run at the end of the month, for example. They don't really care which servers or applications or which virtualization platforms are used to provide those services. They just want it to work. And so what ServiceWatch does is allows us to automate the mapping of all the components, all the individual servers, apps, storage, networks, etc., that make up a service, so that we can answer questions about the health of the service. We can help determine the impact of an incident, an underlying problem on not just one component, but how that component maybe affects multiple services, and it ultimately affects multiple users. ServiceWatch, because it provides this automated service mapping, can also help dramatically improve root cause analysis and troubleshooting and really improve the lives of everyone in the operations center to the point of really streamlining their entire workflow, especially with regards to troubleshooting and remediation. There are also several use cases around change management, again, because of the very accurate and real-time mapping of a service. This really enables folks who are members of the Change Advisory Board, the CAB, the change managers, to look at the impact of historical changes or even to look at the impact of future changes, not just to individual CIs, which of course they can do, but even in a larger sense with continuity planning. And we'll hopefully touch on some of those things in the session, in the demo today. Now, this is all enabled by a top-down discovery, and it's really this very unique, even patented top-down discovery which ServiceWatch brings to market. And this really means that the discovery is defined by an entry point, and this is very different, or a different approach to discovery than the horizontal approaches used really across the rest of the industry. A horizontal approach being one where the discovery is defined by a range of IP addresses, perhaps the whole Class B address assigned to a business, for example. A horizontal discovery would scan through every single IP, looking for a hit, seeing if that IP is then a network device or a server, and if it's a server, inventorying all the apps on the server, so creating a really great asset database. But this top-down methodology starts with an entry point, which is really just a resource that defines how does a user access a service, how does a user touch or interface with a service. That resource could be a thick client hosted on a Citrix server. It could be a web URL or dozens and dozens of other kinds of starting points for a discovery. And essentially what the discovery does is reverse engineers everything that makes that entry point functional. This is largely automated. It's cross-technology, so we talked about all the silos on the previous screens, the IT management silos of databases and VMs and network and other applications. And, of course, this discovery works across all those technologies, as we'll see when we get to the demo and examine a service model in more detail. The discovery is agentless, meaning that it does not require any agents to be installed for the purposes of this discovery. That said, it does use SNMP agents that might exist on network equipment, but for the servers which it discovers, Windows, Unix, or Linux, it won't install any agents on those machines to make the discovery work. Now, just to compare and contrast a little bit and highlight a few things, we won't go through every single one of these, but really to focus on ServiceWatch top-down methodology versus the more horizontal discovery that ServiceNow's discovery provides. or the horizontal the discovery provides there, is that one is focused on service modeling, and the other one is really focused on inventory and asset. It's focused on licensing and populating a CMDB with all the possible CIs across the entire enterprise. So we can see that they're really very different. There's really a very different focus on the one methodology versus the other. One is top-down, the other is horizontal. One's aimed at services, the other one's really aimed at infrastructure and at CIs. And we'll see this as we get into live into the product. So the other things that we can do, of course, once the maps are discovered, once the service model is populated, that model can then be pushed into a CMDB. So the ServiceNow CMDB, while it contains perhaps all the CIs, doesn't contain all the relationships between the CIs to define a service. That's contained in the Service Watch discovery. That can then be pushed. The results of those discoveries can then be pushed into the ServiceNow CMDB so that it can be enhanced with the knowledge or with the understanding of a service model, which then further enables, of course, all the ITSM functionality, the ITSM or the ITIL processes, which sit on top of or derive from the CMDB. Some of the things that we see on the bottom of the screen, such as root cause analysis, change impact, service continuity, while those can be handled to some level inside Service Watch, they can be even further and more deeply enabled in the relevant tools within the ITSM platforms that sit on top of ServiceNow. And of course, monitoring events from various existing monitoring tools that a customer has installed. So those could be network monitoring tools such as Spectrum or Network Node Manager, SiteScope, maybe more on the server side, or Nagios, Splunk for log monitoring. Any of those kinds of tools may be integrated for better root cause analysis and troubleshooting, and we'll see that as well in the demo. We've talked about pushing the service models into the CMDB, and really the key thing to understand here is that CMDB, which contains CIs and a very accurate asset or inventory, is a very different thing from a CMDB, which also has the knowledge or the understanding of the service models themselves. It really provides an entirely different way for IT, for example, to open tickets. They can open tickets now against services, not just a standalone CI. So it really elevates the siloed management approach to the service management approach. And this is especially evident once we push these models into a CMDB. The other aspect of this that's worth discussing in terms of the workload to create these is really around the return on investment. So horizontal discovery tools that populate CMDBs, as we said, populate the CIs, and they may populate the application dependencies, but not the service dependencies. And so that leaves it up to the user then to manually, in some fashion, create the service models. This is really true for really any of the CMDBs in the market today. And this manual effort can take anywhere from a couple days to 8 to 14 days per service. It's a very daunting, very time-consuming task. Now consider and contrast the difference then when mapping or modeling with a Service Watch tool, where services are typically modeled in no more than 1 day. This really offers a dramatic return on investment when compared with the manual method. And then further consider that the manual method implies, of course, that any changes to the service models need to be manually updated. That means that there's likely the case that various subject matter experts who would then help define the changes need to be re-interviewed in order to properly apply those changes. Whereas with the Service Watch methodology, because it's automated, changes are automatically learned or picked up as they occur, and then can automatically be propagated up into the CMDB, keeping the CMDB continually up to date with the latest changes to the service maps. So let's move over and take a look at the live product. So we will be looking at a live instance. Tom, just a quick check. I want to make sure that you can see the service map I'm sharing out.
Okay, Stu. Let's.
Are you seeing the service model okay? Now that I've switched over to the live demo.
Yeah, it looks great, Stu.
Okay,
Perfect.
great. Just wanted to get a quick check on that. Thank you. So what we're looking at here is a service model. This, of course, primarily shows the applications. It's an application-centric view of things. There are a few other things such as storage and load balancers shown on the main map, and we'll take a look at some of the infrastructure components, servers, VMs, hypervisors, and network equipment. It's also part of this service model. The key thing to understand initially, of course, is that this service map is the result of a discovery. It's not the result of manual work with cut and paste, drag and drop. Even the connections or the relationships between these applications is something that's discovered. It's the result or the output of the discovery. We can see the connection definition between two applications here by hovering over it, for example. So, whereas with other tools, it's up to the user to manually create and, of course, understand fundamentally the necessary relationship types such as runs on, depends on, used by. That's not necessary here because these are all discovered. Now, if we look at, let's zoom in a little bit for some more detail. And if we look at one of these components, such as this finance database, we can see that it's hosted on a certain server, SQL01, and that above it, SQL01 shows up again with two other applications hosted on that same server. And this just shows that the discovery is really application-centric. It discovers and models applications. Even multiple applications running on the same server are modeled as individual configuration items or CIs, down to the individual relationships between any of those two applications, as we can see when clicking on the link and being able to understand how those two applications talk by looking at the properties of that connection over on the right-hand side. Now, the other aspect of this that's important to understand is that underneath every application component, every application CI, is really a much deeper discovery. So we see on the right, if we look at the attributes for that SQL Server installation, that it's found how and where it's installed and version and patch. There might be other attributes that are discovered as well, but this is just simply a default set. And the important thing, though, to understand is that the discovery learns about the server hosting the application. And while that might not seem to be any sort of discovery magic, it also finds the virtual machine hosting the server and its attributes. And of course, if it's virtualized, the hypervisor hosting that virtual machine along with the physical server information such as the ESX, as we can see here. And of course, if it's virtualized, then it might as well find, for example, IBM LPARS if it's an IBM environment, or Zones if it's Solaris, Zenware, so on and so forth. So it's pretty agnostic with respect to the types of virtualization environments which it can discover. But the key takeaway here on the right-hand side is that the discovery has learned the entire infrastructure stack, the server to VM to hypervisor stack, which makes the application, the SQL Server, functional. And that's really important. Many discoveries, I would say most, don't understand how to find and accurately map that entire stack. Of course, any changes to this stack will be kept up to date as well in near real time. Now, let's look at a little bit deeper at how the discovery works, and we'll take a look at some of the other components involved in the discovery. And we can see at the top of the service model that the discovery was invoked using this URL as a starting point. This is what's called the entry point. We mentioned that before. We can see it's simply a web URL. So the way this discovery works, The collector, which runs the actual discovery, will essentially reverse engineer the entry point, whether it's a URL or a thick client definition hosted on a Citrix server or some other type of entry point. It will reverse engineer everything behind that URL or behind whatever the entry point is to determine all the components, servers, VMs, hypervisors, applications, network gear, which comprise, which make that entry point functional. And that's really the result of what we see on the screen here. Now, how does it do that? Well, it'll break out the entry point into its component parts, as we see here: host name, IP, port. We don't have host names resolved here in this demo. Protocol, knows to go look for a web server, obviously. So the first thing it's going to do is resolve an operating system such as Unix, Linux, or Windows on this 112 server. And in the process of trying to determine what sort of operating system it is, something else actually has answered and is modeled first, namely this 101 component. What is that, and why did it answer first? Well, it turns out that's a load balancer. And 101 is nothing more than the management address of that load balancer. And the discovery uses SNMP to find load balancers and learn about network gear. Now, 112, which was part of the entry point, of course, turns out to be a virtual IP that's proxied through the load balancer. And the discovery engine, the collector, understands this. So it knows that when the load balancer answers instead of the desired server on 112, that there must be a virtual IP involved. And this virtual IP turns out to be this 112. What's so unique about this discovery is that the load balancer is undoubtedly hosting many virtual IPs, many VIPs. If we say, for sake of argument, there are 100 VIPs hosted, then this discovery is able to ignore 99 of them, meaning that it doesn't need to be concerned with 99 VIPs or their membership. And in fact, it collects the membership for this particular VIP 112. We can see that represented by the 2 on the downstream link here. And learn on the right-hand side that there are 2 servers providing the hosting services, one of them at address 23, the other one at 27. And in fact, if we open up the cluster, and of course this shows that the discovery is cluster aware, by the way. If we open up cluster and take a look at a little bit more deeply at what we're seeing, we can examine one of those servers and see there indeed is the 27 server, one of which is, we expected to see from the VIP membership. Now again, what makes this discovery so unique? Let's say that these 2 servers are part of a server farm, an Apache farm with 100 servers in it. This discovery ignored 98 of them, and it could do that because it carries forward, as it executes the discovery, it carries forward what it's learned previously. For example, the VIP table membership. The VIP table membership, which pointed at servers 23 and 27 specifically, tell the discovery that it can safely ignore the 98 other servers that are part of the farm. And that means that it doesn't need to exercise those servers in any way, not their CPU. It doesn't need to send any network traffic to them. It only needs to discover these 2 specific servers, 23 and 27. And that makes the discovery, as you can probably see, extraordinarily targeted. It's a very focused discovery. And this is what makes it so fast, because it only ever needs to actually discover those components which it's already learned are part of the service. It doesn't need to send out any network traffic to the other components, the extraneous components, which it knows are not part of the service. And it's this sort of algorithmic filtering, if you will, as it iterates from tier to tier, that lets it exclude the non-relevant components and include only those components which are truly part of the service. And it uses that same sort of methodology as it iterates through from one tier to another. Now, if we take this a step further and talk about applications more specifically or more deeply, we can see that by reading configuration information from the Apache server, it knows that Apache talks to these 2, or this 2x cluster of WebSphere installations. We see that on the right. And more importantly, we know that typical application servers are hosting hundreds of Java apps. And if we say there are maybe 400 Java apps running, the question isn't, can we discover all 400? Most discovery engines would be able to do that. The real question is, can we find that individual Java app which is providing services, which is moving traffic for this service called customer management? And because it understands, the collector that is, understands which calls the Apache servers are making to which individual Java apps, it can localize the discovery. It can focus the discovery right down to the individual Java app, this one called trade right here. We see on the right, that's the individual ear. Some people call this the ear file. It's the Java app that's actually doing the work for customer management. And then in turn, by looking at its configuration, it can tell us which individual database instance is being exercised downstream from this. We all know that in most production environments that an application server likely has connections to many, many downstream databases. So if we were to say there are 50 downstream databases connected here in total, we're really only interested in one, and even more so, we're interested in the one database instance providing services for customer management. And by clicking on the link, as we can see here, from the WebSphere cluster down to the database and examining the details on the right, we can see that the discovery has learned which instance is being invoked, where it's hosted, IP and host name, and port and protocol used to communicate with that specific instance. Again, filtering away all the other 49 database servers which might be connected here. This is how specific and how targeted this discovery is. This is the detail which this discovery provides. And consider that what we've examined so far is entirely the product of discovery, not of manual modeling. Now, this is the app-to-app communications that have been discovered here. Let's take a look at how the two servers talk. So the Red Hat server hosting WebSphere and Windows hosting Oracle on the bottom. Let's see how they communicate, in this case across the network. And we can see that the discovery has found all the network devices which comprise the path between those two servers. And just highlighting one of these, we can see, for example, it's a Cisco router. And the discovery will even go down to the interface and port level. As we can see when clicking on a network segment, it's finding source and target port, as we see over on the right. The other thing worth noting is that it will also find connections out to storage environments, as we can see here from that finance database, where we learned that the C drive is actually hosted up in the storage environment. And in a production world, we'd be able to drill into this and see that, or learn which specific volume in the storage environment is providing the hosting for drive C, and even look underneath it and find which LUNs are supporting that particular volume. So that's all the product of a discovery. This entire map was created through that automated discovery process, and we've kind of talked about the components and the methodology for iterating through a discovery like that. Now, there are other use cases that we mentioned before, which are all derived from this, and let's take a look at some of those now. For example, the concept of tracking historical changes. So obviously the discoveries don't run just one time. They run iteratively, or shall we say on a recurring basis. So the VIP tables in the load balancer we looked at, the VIP table might be requeried every 30 minutes so we can keep the membership of the cluster fresh. The routes on a backbone router, we just saw a router in the network path, might only be requeried, let's say, once a day because they don't tend to change very often. And whenever the collector repolls these components and sees that something's different from the previous collection, it knows there must have been a change. It's not looking to see if that change was approved or unapproved. It's just looking to see that there was indeed a change. And it notes that, and we can search those changes because they're all stored historically in a snapshot sort of mechanism. And what I mean is we've drilled into the history bar for this particular service, and we can see that there are a number of change bubbles indicating any changes really any differences from one discovery to the next. So we can hover over those, sure, we can drill into the changes and scroll through them over on the right. The real power of this is that we can bracket around these changes as we see here and click compare to get a snapshot of all the changes which were applied to this business service over this 6 or 7 day period. For example, if we drill in more closely and look at one of these configuration items, the purchase history database, we can see we're tracking a version change on which software, on DB2, the database software, which is driving the purchase history functionality. Just to click another example here, if we look at the message broker, we're tracking a version change not only on WebSphere, but also on the hypervisor. So in this case, we're tracking really two changes, a change to one CI, which is the application, the message broker, and a change to another CI, which is the hypervisor, also happens to be a version change. Obviously, these changes might not pick up only, the discovery might not pick up only changes, it might pick up additions. So CIs which were newly added to the service, newly configured into the service. It might also pick up CIs which are deprecated or deleted from the service as well. So these are all the kinds of changes that the system picks up, not just on the attributes, but of course it could pick up network topology changes exhibited by the network path between two servers, as we saw earlier. So this is invaluable, of course, for change managers, especially folks on the change advisory board, who perhaps need to validate the changes which they had previously approved. Maybe there was already a change ticket open, and let's even assume that the technicians have gone and deployed the changes. How do we validate and verify the changes that they made? Well, now the change management team has a visual way, a very easy way to query and visualize the changes that were actually deployed. Now, that's not the only use case, of course. There's the whole concept of future change as well, and also something that's obviously of great interest to folks on a change advisory board. So let's say that they're looking at the finance database, which is hosted, of course, on SQL Server, and we know that there's a certain version and patch level running, and maybe we've found out that to fix some small problems with a server, we can do that by downloading a patch and then rebooting the server. Well, the question then would be, we know customer management will be impacted by that change, but who else is impacted by that change? There are dozens and dozens of other business services which are part of this business environment, as we see over on the left. If the finance database is a shared component, any one of those services on the left might be using this. And so we really want to know ahead of time if any of them will be impacted by this reboot. And of course, we can click into a what-if screen, which provides that answer. In fact, we quickly learn on the bottom of the screen about all of the services who are dependent on that financial database. So these are the impacted services. We don't know at this point if they'll simply be impacted or if they will actually go down because of this change. But now we have the wherewithal to go research that and certainly notify these business managers in advance of the change. We also can determine that any one of these services uses perhaps some subset of all the components that are directly attached to the finance database. And so this is not a business service, which we see here. This is really a set of adjacencies. What are all the software components which directly connect off of the finance database? And so we see those adjacencies here. Now, if we look at one of the services, for example, EMEA Finance, we can see it uses 3 other SharePoints that are in this environment, and we can click through the different business services to learn exactly which subset of components they use. Now, if we select one of those, let's say the change scenario is that when we when we patch the finance database, we also have to patch and reboot any connected IIS servers. And so now we're looking at a cascading change where change 1 causes change 2. Then, of course, the question would be, who's dependent on the IIS server? And we can quickly learn about those dependencies and see that there are 3 business services which depend on that IIS server. And, of course, we can follow the breadcrumbs back right to our original dependency what-if sort of question. Obviously, we can also determine easily which hosts make up that underlying infrastructure, any network equipment, storage, so on and so forth, that are associated with these applications. So this provides sort of one-stop shopping for analyzing ahead of time the impact of a change that will be made next week, a change to be made in the future. And while this is a software example, the same functionality can, of course, be used to search for hardware dependencies as well, such as a Cisco router or a 3COM switch or a particular server, an ESX server perhaps, that sort of thing. And lastly is the concept of change. This functionality also allows for the definition of change windows. So change windows to a CI or even a number of CIs. These can all be defined here. And the purpose of this, of course, is that we can, when we start looking at the availability of the CIs, and especially the concept of availability as it affects the services, we don't necessarily want the availability to be affected during a known change window. And by entering this change window information, we can exclude those CIs from being counted as being down. Now, if we look at that, and it's sort of a nice segue to looking at the business service from the perspective of availability and up-down status, we can look at all the events which are being brought in and correlated automatically to the service. So, for example, we see events here from Spectrum, from NetApp Storage Manager, and from other sources, and even one from VMware. This is an actual VMware event, by the way, and what's interesting about this is that it represents the kinds of events that you might occasionally see in operations, or maybe even see oftentimes, where the event is cryptic, meaning that perhaps the developers didn't take the time to adequately describe the event. Who knows exactly what this event means? But the fact that we can automatically even correlate these events to the CIs on the map, which are affected by the underlying problem, means that we can learn about the impact of the underlying problem without having to decode the text of the event. And what I mean is, if we select this VMware event and look at the map, let's zoom the map a little bit so we can see the details. We can see there are 4 components. Let's move that around a little bit again. We can see that there are 4 components which are in a problem state because of this underlying issue. So we can see that there is a server FEN and another server -app, each of which is hosting 2 applications. So we immediately know in terms of the impact that without even understanding the text of this event, it's impacting 4 apps on 2 servers. Now, why is that? This event is being correlated to a certain ESX server, so to a physical server. And if we look at one of these components, we can see by scrolling down and looking at the hypervisor that, move the screen around so we can all see what we're looking at, we can see that the actual host which is involved is the ESX4. In fact, if we look at the other server, MOS1 FEN, and look at the hypervisor there, we're not surprised to see that that's also ESX4. So this one ESX4 is hosting 2 virtual machines. Each virtual machine is hosting an IIS and a SharePoint, all of which are affected by this single problem. And so far, we haven't even attempted to decode what this event is. We'll also see that if we drill in more closely to the network link between the 2 servers, that it's also in a problem state. And drilling into the network path, we can see that the network runs through the ESX. In fact, the ESX provides the networking or the switching services between these two virtual servers because they're virtualized on that one ESX. And because the ESX itself is exhibiting problems, that's affecting the network connectivity between these two components, and that's why we see that network connectivity lit up in a problem state. So we've learned all about the impact of this one underlying problem ultimately on 4 applications and 2 virtual servers. I'll point out again without having to decode the actual text of this event. So the correlation of these events to the CIs, the configuration items, which are part of this map, is an extraordinarily powerful troubleshooting tool. And of course, this becomes even more evident when we look at, for example, a cluster which is exhibiting a minor alarm, but see that there's something critical associated with it, only to learn that there's actually one server which is exhibiting all the problems, as we can see here with the Apache instance. But that means, of course, that the other server is healthy and passing traffic. That means the cluster is not actually down. That means the users aren't actually impacted, assuming that the remaining server can handle the full workload. It also tells us something about troubleshooting and root cause analysis and remediation, because do I need to rush out if I'm the manager in the operations center? Do I need to rush someone out to fix this Apache server when the rest of the cluster is actually healthy and still moving traffic and moving transactions? And the answer is perhaps not. In fact, the load balancer is exhibiting, while not critical, some major issues with a chassis down and a configuration problem. And more interestingly here, the discovery has shown us that load balancer is a single point of failure. There's no second load balancer. So if these problems become worse, they were threatening to take down the entire service. And so again, in terms of event correlation and why we want to do this, or why it's so much more meaningful to look at events in the context of the service rather than as individual CIs. As an operations manager, I might choose, because I understand the topology here, to fix the load balancer first, even though it's a lesser level alarm than the critical Apache server. And we've talked about why, since that load balancer is a single point of failure. Now, I might also, as either an operations manager or really anyone in operations, might want to look at these events in the context of the entire business, where each tile represents a business service, and we can then look at these same sets of events, but determine at a glance how wide-reaching they are. For example, if we look at that VMware event, I can see it affects a number of services. And so that might be one that I want to prioritize fairly highly, since if I fix the underlying problem, I'll be repairing issues with all these business services. Similarly, if we look at the Red Hat event with the file system out of space, I can see it doesn't seem to affect quite as many services, for example. And of course here, I'm just ranking the services by priority, where the larger tiles represent the more important services. But of course, since this is a business dashboard and an IT dashboard, I can represent the services or rank them by business metrics such as revenue. Now the larger tiles represent services bringing in more revenue. And when I look at, for example, the Red Hat problem, I can see while most of its effect is on small, very low revenue services, it is affecting this one edit purchase order service, the largest block, the largest tile here, so the one that brings in by far the most revenue. So that may indeed be the one that I need to go fix first because of its potential impact on revenue. So again, the whole point of Service Watch, just to sort of wrap up the concepts here, is to elevate the discussion of changes, of incidents, and even just of CI interactions. It's really to elevate the discussion of all those things from the purely IT level up to the level of the business. And we see that evidenced here by the distribution of these problems across the entire business service, as opposed to being able to identify only an individual CI. So that's what's provided here. In terms of the functionality, we've gone over the mapping, a little bit about the discovery methodology, historical change, and future change. We've talked about the impact of events not only on individual CIs but on the service, and then across the entire business. So Tom, I think I'll wrap up my comments there and see if there are any sorts of questions or follow-up from here.
Thank you, Stu. Thanks for the informative demo, and I hope everyone today enjoyed today's demo and have discovered how helpful Service Watch could be for you to help mapping your IT infrastructure and to your business services, to effectively managing them. As I mentioned before in the beginning, you could reach either Stu or I at tom.malfetto@servicenow.com, or you could reach Stu, Senior Solutions Architect and Consultant at stu.curtis@servicenow.com. In addition, we have Service Watch resources on the product section, or in the product section on the ServiceNow website. So there are pages of information, including a cash demo of today's meeting, as well as white papers and ebooks that will follow shortly, and that will be on servicenow.com/products. So again, thanks for your time today, and I wish everyone a great day on behalf of Stu and I. Have a great day. Bye now.